Section 8.3, we're going to be working with using special products of polynomials. And our learning objective here is how to recognize the special product patterns to simplify multiplying polynomials and make it a little easier. Vocabulary, again, is a repeat of things we've had before, binomial and trinomial. But let's take a look at the special patterns. Okay, so again, we've graphically represented what happens if I take a plus b times a plus b. So I see we've laid this out like a chart. So I've got a and b and a and b. And when I multiply a and a together, I get a squared. When I multiply a times b, I get ab. And when I multiply b times a, I also get ab. And b times b is b squared. And that's what we have here for the square of a binomial. Right? So a squared plus 2ab plus b squared. And if we were going to have a minus b, the only thing that would change is this sign here. And in fact, you see that if b is negative, you change it to be addition. And when you substitute negative b in place for b, it works out to be exactly what I said. You'll notice this sign and this sign match. Okay, so what we want to get in the habit of doing is identifying this particular pattern. And I can do that by saying, is this first term the perfect square of something? Yeah, this is the square of A. And is this term the square of something? It's the square of B. And then is the middle term 2 times this times that? Okay, so that's how we identify it by looking at the problem. So if I wanted to go ahead and square it, right now I'm just going to multiply. I'm leading you into factoring. So we want to be able to multiply it, and we want to also be able to factor with it. So I'll have a squared. So in this case, a is 6b, and b is negative 1. So and I'm going to have this item squared, so that's 36b squared, minus 2 times negative 1 times 6, that's minus 12b, and negative 1 squared is plus 1. Okay, so all I did is I took this pattern here, and I plugged, actually I took the top pattern, and I plugged 6b in for a, and I plugged negative 1 in for b, and I simplified. Okay, now we also have the difference of two squares, right? In the difference of two squares, a squared minus b squared is always made by multiplying two binomials together, a plus b times a minus b. And these guys are called conjugates, and they have some important purposes. So it's important also that we get used to working with these things. But when I see that that this item and that item are the same, and this item and this item are the same, and the only thing that's different is this sign here in the middle, that's the sign that I can move right on to the difference of two squares. So it's going to be the quantity 3s squared, that's an s, minus the quantity 8 squared. So that's going to be 9s squared minus 64. Okay, so this is what we call the difference of two squares. If we go ahead and start multiplying these guys together, you can see, oh, this one here, this is going to be the difference of two squares, so it's going to be 2a squared, which is 4a squared, minus 5b squared, so that's 25b squared. Right here I've got the square of a binomial, so I have the first term squared, that's 36x squared, plus 2 times 6x times 5. Well, 2 times 5 is 10, times 6x is 60x, and then I'm going to have 5 squared plus 25. Oh, and if we look at this, I'm doing a little mental math, I can take 2 times 280, right? Or sorry, 2 times 28, which is 56, and 30 times 28, right? So 3 times 8 is 24. And I'm leaving a space because I'm multiplying by 0, right, by 30, not by 3. And if I carry the 2, 6 plus 2 is 8. And I add them together, I'll get 6, 9, 896 for 28 times 32. So one thing I'm doing there is I'm essentially taking this and saying, well, this is 2 times 28 plus 30 times 28. Okay, and it helps me break it into small parts that are easier to do. Okay, applying this on into a different type of a problem with a real world kind of wrapper on it. We see that when we're talking about these dogs, these border collies, the color of the dark patches on a border collie's coat is determined by a combination of the genes of the parents. So an offspring inherits one patch color gene from each parent. Each parent has 2 color genes, and the offspring has an equal chance of inheriting either one. So you've got B for black patches and R for red patches. So you see when we have B and R in this parent and B and R in that parent, then we get the same sort of the square of a binomial here as our possibility here. Okay, so supposing that each parent has the same gene combination BR, this is called a Punnett square, this little graphic arrangement, shows the possible gene combinations of the offspring and the resulting patch color. What percent of the possible gene combinations of the offspring result in black patches? Right, so any gene combination with a B, so this one has a B, and this one has a B, and this one has a B, so 3 of the 4, that would be 75%, 3/4. And if we talk about using a polynomial to model the possible gene combinations of the different offspring, right, we know we're going to have b squared plus 2br plus r squared, okay, as this possible gene combinations. Okay, so I'm sorry, I've already gone ahead and worked with this. So if we model the gene from each parent with 0.5b and 0.5r, right, then we know we'll have 0.5b plus 0.5r, meaning there's a 50% chance that they've got a b and a 50% chance that they've got an r, right? And we take that quantity and we square it. So I'll have 0.25 b squared. And then here in the middle, I'll have 2 times 0.5 times 0.5, right? 0.5b times 0.5r. So that's going to be 0.5 br plus 0.25 r squared. Okay? And that's just working through how we could create a model that would shape what would be likely to occur. And that's 8.3.